This is part 7 of a series on KNN. In this video, we'll look at KNN regression. This video was produced in Korean and then translated into English. The audio was generated via AI text-to-speech. In the last 6 videos, we looked at the KNN classification algorithm. In this video, we will look at the KNN regression algorithm. Let's look at the KNN regression models using the simple average and weighted average methods, and implement the models in code. And let's see how the regression results change depending on the k-value setting. Finally, let's implement KNN regression models to predict the house prices in Boston. Now let's look at the KNN regression algorithm using the simple average method and the weighted average method. First, let's look at the data. We have the following training and test data. This is one-dimensional data with one feature x. Both feature x values and target y values are continuous real numbers. The test data contains only x values and no y values. Our goal is to predict the y value of the test data point using the training data points. X is the independent variable and y is the dependent variable. Normally, this value can be predicted using a linear regression model, but here we will predict this value using a KNN regression model. If we plot this data in a two-dimensional space, the xy plane, it looks like this. When x is 1.2, y is 5.28, and when x is 2.5, y is 2.33. This test data point will lie somewhere on the line where x is 12.0. To predict the y value of this test data point, we find the k nearest neighbors around this line. For example, if k is set to 4, these 4 training data points will be the nearest neighbors to the test data point. We use these 4 training data points to predict the y value of the test data point. There are 2 ways to predict the y, the simple average method and the weighted average method. The first way is to compute a simple average of the y values of these 4 training data points. In the table on the left, these data points are the 4 neighbors. Taking a simple average of these 4 y values gives 17.85. This is the predicted y value for this test data point. Then this test data point will be located at this point in this space. If a test data point is located here, these 4 training data points will be used as neighbors. Next, let's look at the weighted average method. These 4 nearest neighbor data points are as follows. We compute the distances between this test data point and its 4 neighbors. The x value of the test data point is 12.0, and the x value of the first neighbor is 10.1. Since this is one-dimensional data, we simply compute the difference in the absolute values of x. If you have multiple features x, you can use this formula to compute the distance. We looked at this formula in the second video in this series. We assign higher weights to neighbors that are closer to this test data point, and lower weights to neighbors that are farther away from this test data point. Since distance and weight are inversely proportional, the weight can be defined as the reciprocal of distance. Taking the reciprocal of these distances, the weights are computed as follows. The total sum of the weights is 4.03. If we compute the weighted average of the neighbor's y values with these weights, we get 18.32. Then the predicted y value for this test data point will be 18.32. If you use the weighted average method, you can set the k value to a large value. This is because the weights of distant neighbors are small, so their impact on the prediction y is small. Therefore, using the weighted average method can provide more stable predictions. Next, let's implement a KNN regression model using the simple average method. Generate the training and test data. The number of training data points to generate is 1,000. And the number of test data points is 100. We generate 1,000 random values between 0 and 1 for the independent variable xtrain. And generate sin x values with Gaussian noise for the dependent variable ytrain. This is the training data. If we plot the training data on the xy plane, it would look like this. And we use NumPy's linspace function to generate 100 test data points. We want to predict the y values of this test data using a KNN regression model. If a test data point is located here, the average of these neighbors will be the predicted y value. If we predict the y values of all the test data points in this way, we get a sine-like curve like this. Next, we generate the distance matrix between xtest and xtrain. We took a closer look at the distance matrix in the first video of this series. Next, we find k nearest neighbors to the test data points. The k value was set to 20. This code is the one we used in our previous KNN classification model. Next, we predict the y values of the test data using the simple average method. Next, we plot the training and test data points along with the predicted y values, ypred1. The results are as follows. The blue dots are the y values for the training data points, and the red curve is the predicted y values for the test data. As expected, we got an approximate sine curve. Finally, let's predict the y values of the test data using scikit-learn's Kneiber's regressor. Create a KNN regression model and fit this model to the training data. And then predict the y values of the test data, ypred2. This model uses the simple average method by default. The results are as follows. This is identical to the result on the left. Let's run this code. The results are as follows. The first is the result of the model implemented from scratch. And the second is the result of the model implemented using scikit-learn. You can see that the two results match well. Next, let's implement the KNN regression model using the weighted average method. Up to this point, the code is identical to that on the previous page. Since the weighted average method allows the k value to be set large, we set k to 200. Next, we compute the weights to apply to the neighbors. The weights are the reciprocal of the distances. Next, we use the weighted average method to predict the y values of the test data. Next, we plot the training and test data points along with the predicted y values, ypred1. The results are as follows. Finally, let's predict the y values of the test data using scikit-learn's K-neighbors regressor. Create a KNN regression model. If the weights argument is set to distance, the model uses the weighted average method. Fit this model to the training data. And then predict the y values of the test data, ypred2. The results are as follows. This is also the same as the result on the left. Let's run this code. The first is the result of the model implemented from scratch, and the second is the result of the model implemented using scikit-learn. You can see that these two results also match well. This time, let's look at how the predictions for the test data change as the value of k changes. First, let's look at the results predicted by the simple average method. We can see that when k is too small, overfitting occurs, and when k is too large, underfitting occurs. It seems that we need to find a suitable value of k between 10 and 100. Next, let's look at the results predicted using the weighted average method. You can see that when the k value is small, overfitting also occurs. But when the k value is large, underfitting does not occur. This is because neighbors far from the test data are given small weights and have little influence. This model is less sensitive to the value of k, so k can be set to a large value. Next, let's use a KNN regression model to predict the house prices in Boston. Load Boston house price dataset. This data consists of 13 features. And we split it into the training data and the test data. Normalize the data using the z-score method. Write a function that visually displays the actual and expected prices. Next, we create a KNN regression model using the simple average method. We fit this model to the normalized training data. We predict the y values of the normalized test data and restore them to their original scale. Then we visually compare the actual y values of the test data with the predicted y values. The results are as follows. The x-axis represents the actual y values, and the y-axis represents the predicted y values. This result shows that the correlation between the actual y values and the predicted y values is very high. This means that the predictions are somewhat accurate. Then we measure the R-squared score. The R-squared score was 0.751. For R-squared score, please refer to the linear regression series. Next, we create a KNN regression model using the weighted average method. Then we do the same thing as above. The results are as follows. The results are similar to the left. Let's run this code. We got the following results. Finally, let's compare the performance of different models in predicting Boston house prices. We randomly construct the training and test data from the Boston house prices dataset. We perform regressions on the training data and measure the R-squared score on the test data. We performed 10 regressions for each model. The measured R-squared scores are as follows. These are the average scores for each model. These are the results measured using the linear regression models. For more information on these models, please see the videos in the linear regression series. The R-squared measured by the KNN regression models with the simple average method and the weighted average method are as follows. KNN regression showed similar performance to OLS or TLS for linear regression. So far, we have looked at the KNN classification and regression algorithm through a total of 7 videos.